Algebra 2 honor students, this is going to be your notes on solving rational inequalities graphically. So if you turn to page 25 in the packet, there are some quick examples that we're going to fill in of the solution sets to some rational inequalities. So we're comparing a rational function to a constant, or over here we have some variables as well. And what we're going to do is we're going to use the critical values provided on the graph to help us solve this partitioning and these inequalities. So the critical values that we're really talking about are, you can see how that x-intercept is labeled in number 1 and number 2 and the others down below, and then also where the vertical asymptote is located. Now, something I'm hoping you remember about vertical asymptotes is the vertical asymptote comes from the value that makes this denominator undefined, which is why x equals 3 is a vertical asymptote. Certainly plugging in 3 would make that denominator undefined. So the one thing I want to point out about each of these examples today is that you're not necessarily seeing the graph of x plus 1 over x minus 3. You're seeing the graph of x plus 1 over x minus 3 plus 2. And now we're going to solve when that's greater than or equal to 0. So when we get into our next lesson, which we'll be doing this algebraically as opposed to looking at the graph, this will be a key point, is to set it to 0 first, because it makes our job so much easier to determine the solution to this inequality. This is what you're actually seeing graphed here, this equation right here. So if I want to know where this is greater than or equal to 0, I'm looking for where is the graph positive. And positive means where it's above the x-axis. So you can see that the graph is positive in this section right here up until the x-int at 5/3. And it goes negative, so we don't want to include that. But then all of this region up here, that's all going to be positive as well. So the solution to number 1, just looking at the graph, is negative infinity to 5/3. Now we can include that root at 5/3 because we also can include where the function equals 0, and that's at 5/3. Union, then on the other side, when I get past the vertical asymptote at 3, we're going to say 3 to infinity, but notice how we can include 3. 3 is definitely where this is undefined, so you'll never include the vertical asymptote, but sometimes we might include the root. And I say sometimes because you can only include the root if your inequality includes the equal to 0 part. All right, so that's the main idea for today, and that's why I think this lesson will go pretty quickly. In number 2, you're not looking at this rational inequality graphed. It's if you were to subtract x and subtract the 2 over. So really what we're looking at is x squared minus 3x plus 2 over x minus 3, where if I subtract the x and subtract the 2 over, now we're comparing to see when this is less than or equal to 0. Okay, so that's the inequality that we're solving based on this graph below. If we're looking at less than or equal to 0, we're looking this time at where is the graph negative. Less than or equal to 0 would imply we're looking for the negative. So wherever we're below the x-axis, that's where the graph is negative, which is all of this here up until the vertical asymptote at x equals 3 again. Yep, notice how x equals 3 makes this undefined. And then once I jump over the asymptote, I'm positive just for really a short time, but once I go through the x-int at 4, it's negative over this interval as well. So highlighting these regions might be nice in terms of being able to efficiently write my solution, which for this one would be negative infinity up to the vertical at 3, but don't include it. And then union, our x-intercept, we can include 4 because of the equal to 0 in the inequality. So union, then everything from 4 to infinity. Mostly a negative function, isn't it? It's mostly below the x-axis, except for this tiny portion between 3 and 4 when the graph is, in fact, positive. Once you get the idea of this process, you could probably do the next 2 on your own. However, I'll walk you through them quick, and then next time we're in class, we'll do some more practice together. If you look at number 3, we're looking at where this is less than 0. Nice thing is that this is already set to 0, so there's nothing I have to like move over to the other side to kind of consider, you know, what we're looking at, whether it's greater than or less than 0. And less than 0, like we saw up above, we're looking at where the graph is negative. So the graph is negative in this whole section over here, right there. And it's negative over here as well, to the right of that root. All of this is positive and above the x-axis. So where are we less than 0? Well, from negative infinity up to the vertical at negative 3 this time. We never include a vertical. Should I include the root this time? So we're going to go union 1 to infinity. In the other cases, I've included that root with a bracket. However, since I want strictly less than 0 and not less than or equal to 0, we don't want to include the root. So it's a little bit picky in terms of notation, but welcome to mathematics. Okay, we want to make sure that we list that solution set appropriately by not including the root at x equals 1. Okay. And last one over here, if you were to subtract the 1 over, we're now comparing this to 0. In fact, we're comparing to see when this function is greater than or equal to 0. So we can include the root this time. Greater than would be the positive section, which is all of this. And then everything to the right of that solution at 3. So the solution for this last one in number 4 would be from negative infinity up till the vertical at -1. And then union greater than or equal to 0 would include 3 to infinity there as well. We can include 3 in a bracket. The last thing I want to do, I realize that we're done with this page, but what if I had said instead of greater than or equal to 0, what if I said less than or equal to 0? What if that was the inequality? And the only reason I want to say that is that all of our solutions here today had 2 inequalities in a union, but it doesn't have to be that way. Less than or equal to 0 would just be the negative part, right, which would be all of this. So if I said less than or equal to 0, I would only be able to go from the vertical asymptote to that root. It would be from -1 to 3 with a bracket, and that's it. So keep in mind, not all rational inequalities have a union of 2 different sets. It could just be an interval where the graph happens in between the vertical asymptote and your root, and that's it. So just a quick note about that to make sure we're on the right track with rational inequalities. We will do more practice with rationals in class, a little bit more graphing, some word problem examples next time I see you. Let me know if you have any questions.